Finally, we get to take all of the information we've learned about functions and their graphs and apply them to real-world problems. Now, you may have called these things word problems in the past, but we're going to call them mathematical models of the real world. Constructing functions, because that's what you do in a real problem. You look at the information that's given to you and you construct a function that will describe that information, and then you can answer questions based on that function. So that's what we want to do here. And this will be the very last part of this unit, so we can end up with some nice practical problems, I hope. So, on that note, mathematical models, constructing functions. There's some general advice I'm going to go ahead and write down now. You'll hear me say other things as I do the problems, but here's some general advice. And this is common sense sorts of things. First of all, carefully read. Mathematics problems have certain pieces of information and certain phrases that you need to learn to cue on. And as we do more of these, you'll begin to see what those are. But you have to carefully read what's given. And always sketch and label something. Try to draw a picture of what's going on. In practical problems, drawing a picture is almost essential to understanding. And I don't understand why a lot of folks would rather not draw pictures. Draw pictures and be bold about it. Draw them large. Don't make thumbnail sketches that are so small no one can read them. Make big pictures, and you'll find that that helps you think about the problems. Thirdly, you want to show all your work. Again, people like to hide their work sometimes. The problem with that is there's no way to tell if there's an error, where the error occurred, if you haven't left a paper trail for us. And for yourself. Remember, the first person who looks at your work the second time is going to be you. When you go back and study it for a test or for a final, you want to have work that you can follow. So show all of your work. Put in all the steps that you think you need to understand it. And of course, practice. Now, this VSI course allows you to practice, but take this to heart and do a lot of these as much as you can. All right, let's go ahead and bring our first problem here. Nice, easy problem to get us warmed up. Here's the first problem. The perimeter of a rectangle is 50 feet. Now, remember what perimeter is. It's the distance around the rectangle. So the perimeter of the rectangle is 50 feet. Even before I do anything else, I know that when I start solving this problem, I'm going to draw a rectangle. I'm somehow going to mark 50 feet somewhere. Express its area, A, okay, so I'm interested in area, as a function. Function. Now that's a word we've been studying in this unit. A function of the length x of a side. The length x of a side. Well, there are 4 sides to a rectangle. What could this possibly mean? Well, evidently we need to draw a picture and decide what this means to see if it's ambiguous or not. So let's put this to the side and let's start our solution. And as I said, the very first thing I'm going to do is draw a rectangle. So here it is. And I'm going to remind myself that I'm going to be interested in area. So I'll even do a little shading here because I like my pictures. Okay, there's what I'm interested in. Now, I was told that I want it to be a function of the length x of a side. Well, let me suppose I label this side x. By the nature of a rectangle, I know that the opposite side is also x. However, I don't know what the other 2 sides are, but I do know that they're equal. So I guess temporarily I can label them by some letter, maybe like W, W standing for width, or any letter that you like. Now let's go back to what we had here. Let's see. The perimeter of a rectangle is 50 feet. Let's translate that into a mathematical statement. That is the first thing we need to do in creating a mathematical model. Take the words, translate it into mathematics. Perimeter. Perimeter, as I said, is the distance round the rectangle. So I go W, X, W, X. So I have 2 X's and 2 W's. So 2X plus 2W is the perimeter. Well, you know, I just can't help myself. Whenever I see something I can factor out, I just do it. I don't know if it'll be helpful, but I just have to do it. It's a good habit to have. Now, what else do I know? Oh, yes, the perimeter, which is this formula based on the picture, is equal to 50. And I don't need to mention the units right now, maybe later. So I know that 2 times x plus w is 50. Well, that shouts out something to be done too. There's a 2 on both sides of this. I have just got this uncontrollable desire to divide out 2. So x plus w is 25. Now with that, I begin to feel a little more confident. Remember, the problem was to express the area as a function of the length x of a side. Not the length w, but the length x. W is a letter that I introduced. I'd like to get rid of w. I'd like to write w in terms of x. Well, with an equation like this, I can, can't I? W, therefore, is 25 minus x. Now, it's possible you saw this all a lot earlier, but there's a point here. You want to get all of this information written down somehow. And if you didn't see it earlier, now you see why I did it. Okay, so what was I looking for again? I was looking for area. Area is the most important thing to me in this problem. So area, which I'm currently labeling A, is equal to what? Well, the area of a rectangle is easy. I remember that from the basics, if you recall. It's simply x times w. So it's x times, but wait, I know what w is. Here's w right here. It's x times 25 minus x. Now, the advantage to doing what I've just done is, notice that over here, there is only one variable, the variable x. So that means this a over here, which is normally the way things are written, a single letter, certainly the way things are done in some of the sciences, we can now write this as a function. We can say a is only in terms of x, so I can call this a of x. So I've added that now. And so I have a function. A of x is x times 25 minus x, and that's what I was asked to do. I was asked to write the area as a function of a side. Now, in the problems that we're going to look at coming up, we're going to go ahead and graph these. I won't graph it right now, but in the other ones we will. I've got another one set up here, and here's what it reads. Let P, which will be a point, xy, it'll be a point on the graph of y equals x squared minus 1. Now wait a second before we go any further. X squared minus 1, that ought to be a graph that you can see in your head. You can say to yourself, x squared, I know that graph. That was one of those important functions. Minus 1 is a vertical shift downward. So I know what the picture looks like before I do anything else. It's helpful as you work through here to see if you understand what's going on. So let P, xy be a point on this graph. Okay, what do I want to do about that? A, I want to express the distance, which I'll call d, from P to the origin, which is 0, 0, as a function of x. Okay, that's one of the things I need to do. Then what is d if x is 0? So I'm being asked for a specific d value when the x value in the function is 0. Okay. Finally, down here, I want to graph d of x. D will be a function of x, so this is a legitimate notation. I want to graph this and estimate at what x it, meaning the d function, has a local minimum. So I've got my work cut out for me. But before I do any work on this, we'll leave this on the screen for a beat. I want you to try it. See if you can come up with the graph of the function, pick an arbitrary point, write down what you might think is the distance function, see if you can answer part B, see if you can come up with a graph, and maybe pick out where the local minimum is. Try all of that. If you get stuck, don't worry about it. I'm going to do it as soon as we come back. But we'll pause for now for you to try. I hope you've had a good time, and I hope you've been successful. Now we'll see how I would have approached this problem. Here is the situation. As I said, one of the first things I noticed is that this is x squared minus 1, a shift downward of x squared. So this is the first thing I'm going to do is draw that picture, because it probably has bearing on the problem. So, solution. I'm going to notice, or recall, or recognize that y equals x squared minus 1 is just x squared v shifted, use my little shorthand there, vertically shifted down, by 1. So in the picture that I can use for all of my work, I know that the x squared function is that parabolic shape, and now it's shifted down by 1, so it's going to look something like this. So this will be the curve. You want to label your curves, always do this, x squared minus 1. This is the x and the y axes. Down here where it strikes here, I know is minus 1. I've shifted down by 1. And going back to the problem, I want to mark a point P on the graph, anywhere. So I'll just pick a point here. That'll be my point P. It's the point xy. But I can do better because I know what y is. Y is x squared minus 1 on this curve. All the y's are the same, x squared minus 1. So this is the point x, comma, x squared minus 1. Now that specificity will help me as I work through this. Okay, I have a nice picture now that I will continue to refer to, but let's start answering some of the questions, or on the path to answering them. Question A. We bring back the original problem here. Express the distance, d, from P to the origin as a function of x. Distance between this point P and the origin. I know how to find the distance. I have a distance formula. So let's see. Distance from P, which remember we've rewritten as x squared minus 1, to 0, 0 is, and this is the distance d. Now I hope to write this as a function of x, but I don't know that it is yet. So let me just pause and leave it as a d. Leave a little space there. Now I know the distance formula. It's a big square root, and it's the difference of the x's, x minus 0 squared, so x minus 0 squared, plus the difference of the y's, so it's x squared minus 1 minus 0 squared. Now, you may not think that I needed to do that with the zeros, but at least I've got the form correct. Now, the first thing I'm going to do, of course, is simplify it. So that'll be x squared plus the quantity x squared minus 1 quantity squared. And by the way, since everything involves only x, I can go back up here and write this as a function of x, d of x, which is what I wanted to do. Now, there's no reason for me to go any further with simplifying this, but maybe later I would want to have it simpler. So why don't I put in brackets here the simplification where I multiply this out. So I'll have x squared plus squaring x squared minus 1 will give me x to the 4th minus 2x squared plus 1, all under the square root. And of course I can simplify that by making x to the 4th out front minus x squared plus 1. So simplification is something that if you can do it without too much trouble, go ahead and do it. You never know when it'll be useful. So either this form or this form is okay at this point because we don't know what else we're doing. So I have d of x written as a function of x. Excellent. Let's go ahead and look at b. We can slip in b down here because it's short. Remember what question b was. What is d if x is 0? Well, now that we have d as a function, d of 0, putting 0 in for x, we see that d of 0 is going to be, now any of these forms would be fine. I'm going to use the last one because it looks simplest to me. Square root of 0 to the 4th minus 0 squared plus 1. Well, that's easy. That's the square root of 1, which of course is 1. So d of 0 is 1, and I have answered question number B. Now let's get to the one that I find most interesting. C. And let me rewrite the function d of x, and I'll use that shortened form, x to the 4th minus x squared plus 1. And let me remind you again that if you don't like the square root symbol, or you can't use it very well on your calculator, you can always rewrite this as x to the 4th minus x squared plus 1 to the 1/2 power. So please be aware that that's always an option. Now what I'm going to do is I'm going to graph this. Why? Well, the question was, if you recall, C, graph it. That was one thing. And then we want to estimate a local minimum. That's going to be quite easy once I get to a graph. So I want to graph this. Okay, I can graph this. I can type this into a graphing calculator. That's no problem. I would like to have some idea of a window to use. and let's see if I can come up with one. I want a window, and we write our windows this way, with the x interval here and the y interval here. And based on the sketch, remember the sketch? Let's look back at the sketch. Here's the sketch P. Now, remember what we're dealing with here. Here's the origin. We're looking at this distance here. And we want to know when that's going to have a local minimum, when it is short as possible. Now let's think about this. How small can any distance be? Well, a distance can't be any lower than 0, so we could say that that's a lower bound. And how big will this distance get? Well, if we look at various distances around the origin, notice that we can go as far as 1 here, and around the origin it stays pretty short, but as we get farther and farther away, as we go further up the curve, the distance gets quite large. So we're going to need to cut it off somewhere. Since this looks like a distance 1 here, let's just say we cut it off at 2. So my x values for the function that I'm about to graph, this distance function, let me just guess 0 to 2. I needed some place to start. That seemed reasonable. And since the y values, the distance, of course, will be 0. The x value 0 to 2 and the y value 0 to 2 is probably worthwhile looking at. If that doesn't work, we'll change the window. Okay. Well, with this in mind, it's time to go ahead and look at a calculator picture of this and then come back and give a sketch of it. So let me bring my calculator over here. And as it appears on the screen, zooming in toward you, I hope it's bright enough for you to see. This is my calculator, has a place where I can enter equations, and this is that place. And you see I've entered square root of x to the 4th minus x squared plus 1, which is our distance function. And now I've already set the window up. We can look at the window. There's the window. You see x min is 0, x max is 2. Going on down, y min is 0 and y max is 2. And then we can go ahead and look at the graph now. Now there's the graph as we go in that region. And you can see as we go off to the right, it's growing. Right? It's growing up toward the right, which means that it's going to continue to get bigger. We saw in the picture that as points got further and further along the curve, the distances would get longer. So we can ignore anything happening out there. It's just going to get bigger. So it looks like the minimum is sitting in there, somewhere where that little dip occurs in the middle. Now on my calculator, as you have an analogous one on yours, there is a place, minus second calculator, and I can come over here and I can get minimum. And then by hitting enter, it says it's calculating and it will look for the minimum point for me. Now I know you have one like this on your calculator. If you can't find it, you can use your trace key and simply trace to the middle. Now when this is done, there will be x and y values indicated. If you can see that down there, the x value is about 0.707, the y value is about 0.866. So now what I'm going to do with this picture, and this is what you do if you have the picture next to your piece of paper, you draw it. I will go ahead and draw it for you as we move from the calculator back to the pad. So here's what I will do, and you will often have to do on your own papers because you've got to verify that you've got the picture. Here's the picture we had going from 0 to 2 and 0 to 2. The picture looked something like this. It had a dip here and then went off and grew. And down here at the dip, which was the minimum point, we found that the x value was approximately 0.707 and the y value here was approximately 0.866. And what are those values? This value here, of course, is the local minimum that we were looking for. And what does this all translate into? Well, this axis is the x-axis. So this is an x value. So when x is 0.707, I'm going to have a point on the curve that is minimum distance from 0, 0. So if I look back at the picture, and I've got several lines on there, but if I look back at this picture and I ask myself, where's 0.707? It's going to be some point in here, which means I'm talking about a point down here somewhere. If I go to that point, and that's not quite right, is it? I guess I'll need to adjust my picture a little bit. Because, remember, we found out, yeah, that's all right. There's a point about there, and down to the picture, this distance here, I'm right, is going to be the minimum distance. because this x value here is about 0.707. And that's what this graph tells us. So we've done a nice bit of analysis here. We've used the calculator appropriately. Since we don't have calculus, we can't find that local minimum using a calculus technique. But the calculator allows us to find it, either by tracing, or by using that jump function or my function, which took me to the minimum. And with that approximation, I'm satisfied with what I have at this point, and that's what I wanted to do in this problem. So let's move on to a second problem, or a third problem, I guess. Here's another problem to look at. This one's a little bit more geometrical. Consider an isosceles triangle. Now, isosceles, in case you don't remember, isosceles is a triangle in which two of the sides are the same length. Now, it's possible that all three are the same length, but that's not necessary. What's necessary is that two are the same length. So an isosceles triangle of fixed perimeter, P. So P is a constant here. We'll later replace P by a number, as you'll see down below. But for the time being, we'll just consider it a constant. Okay, so I've drawn a picture over here. Here's an isosceles triangle. These two sides are the equal sides. And if P is the perimeter, the distance round, well, if you take away two x's, you have P minus 2x. And that must be the length of the third side. So that's why I've labeled this third side P minus 2x. Okay, what do we want to do here? First, A, we want to express its area as a function of x. Okay, we'll look at that. Secondly, what is the domain of that function, that area function? We'll look at that. Then in C, we will start out by supposing that P is 4. We'll put an actual value in for P. And then, once we have done that, we can graph A of x, because A of x will only have one variable, x. And then we'll estimate where it has a local maximum. Where will the area be largest? So this is the problem we now want to look at. Okay, let's start looking at this. Solution. First thing I'm going to do is redraw that picture, because I know it's going to have bearing on what I'm doing. So here's my picture. Here's the three vertices. This is x and this is x. This distance down here I've labeled P minus 2x, because the known distance around is P, fixed constant, and I subtract away x to get the third side. 2 x's, that is. Okay, so there's my isosceles triangle. Good. Let's look at point A, which was to express the area as a function of x. Now let me remind myself what the area of a triangle is. Area, which we'll call A, is equal to 1/2 the base times the height. We saw this when we discussed basics earlier in this course. So that's 1/2 base times height. Okay. Well, we could go so far as to write 1/2 P minus 2x, but when we get to the height, we are stuck, because we don't have a value for the height. What would the value be? Well, let me dot it in. It is the distance from the vertex perpendicularly downward to the base. If I call that h, then I want h in here, but I don't know what h is just yet. So I have to do a little work. If you see what I have here, let me take this triangle and move it down here. I have a little right triangle. This side is h, this side is x, and this side is half. Because this is isosceles, this is going to cut the base in half. This side is half of P minus 2x, so it's 1/2 P minus 2x. So I have all three sides. Well, I have all three sides labeled, that is. I know the x side because x is the variable I'm using, and I know the bottom because P is known, and x is the variable I'm using. H is the one I don't know. Well, by the Pythagorean theorem, I can find h. So let's do that. By the Pythagorean theorem, which we saw back in basics, we know that h squared is equal to x squared minus 1/2 P minus 2x quantity squared. Because h squared plus this squared is equal to x squared, and if I solve for h squared, this is what I get. So, continuing on down here, h squared is what I'm looking for. Continuing on down, I multiply out the right hand. x squared minus 1/4, that's the 1/2 squared. And then the binomial p minus 2x in here I square. I get p squared minus 4x plus 4x squared. Doing all the squaring there. Oh, sorry, minus 4xp. Don't want to forget my p. And then if I multiply all of this out, things are going to work out a little bit nicer. X squared minus 1/4 p squared plus xp minus x squared, because the 1/4 times each of these 4's gives me 1. And so I have x squared and minus x squared, so they cancel each other out. And I'm left with, let's see, and put this in the other order, xp minus 1/4 p squared. And I can take one last step down here and factor that p out. So p times x minus 1/4 p, period. So h squared is equal to this. And I think it's time for me to move to another page. But if h squared is equal to this, then h being a length is equal to the square root of this, the positive square root. So let me carry that on to the next page. So h is equal to the positive square root of p times x minus 1/4 p. Thus, now that we have h, we can finally write the area. We can write area A is equal to 1/2 p minus 2x. That was the 1/2 base that I had in there earlier. And now I can put in the h. Square root of p, x minus 1/4 p. Okay, that is the area A in terms of x and the constant p. All right. One more item here. We'll talk about the domain of A. And the domain of A is going to be all the x's that are allowable in here. Now, there are two ways to look at this. The first is the only restriction from the area function, which we just wrote up here, from the area function is that, well, remember, we don't want area to be 0. We want area to be a positive number. And we have a square root here, so the square root, object under the square root, must not be 0 and must be positive. So we must have p times x minus 1/4 p greater than 0. That's necessary for the formula. Now we already know p is the perimeter. That's a positive number. So that means we just need x minus 1/4 p to be greater than 0. In other words, x is greater than p over 4. Now p is a known constant, remember, so I now have a lower bound for x. I can get an upper bound also. Also, from the triangle itself, using an abbreviation for triangle, since p minus 2x is a side length, remember the original triangle? Here's the original triangle, and p minus 2x is the length of a side, so we don't want it to be 0, and it certainly can't be negative. P minus 2x must therefore be greater than 0, which is to say p is greater than 2x, and if you divide by 2, that means x is less than p over 2. And there we have an upper bound for x. Hence, the x's must live in that interval, which means the domain of A is equal to the interval from p over 4 to p over 2. P over 2 is that upper bound we just found, and p over 4 is the one from the other page. Now, we're working on part C of this problem. Part C, we will take p to be equal to 4. Now remember, p is the perimeter. In fact, let me go ahead and draw the triangle again here. This was the isosceles triangle whose area we're looking for. And remember, we labeled the two sides that are the same by x. And now this was p minus 2x on the bottom. We'll now label it 4 minus 2x, because p is now 4. Okay. Well, that means we're going to want to write down the area now without any of those p's, but with 4 in place of p. And just so you remember, let me bring back the area formula here, which I've got written out neatly 1/2 times p minus 2x times the square root of the quantity p times x minus 1/4 p. And the domain of this function is p over 4, p over 2. With that in mind, let me go ahead and fill in those blanks, those p's, with 4's. So we'll have 1/2 4 minus 2x times the square root of the quantity 4 times x minus 1/4 of 4. Now, that's the area function, and it's perfectly correct, but you know, I see things that I could simplify, so I'm going to do it right away. It's always good practice to do it immediately. I see that 1/2 times 4 here would give me a 2, and then the 1/2 carried through times the minus 2x would give me minus x. The square root here, of course, breaks apart over the product. The square root of the first part, square root of 4, is just 2, and the square root of the second part is simplified because x minus 1/4 times 4 is 1. So that's x minus 1. So this is the area function we're going to deal with in this part. And let's go ahead and write down the domain where x is in the interval 4 over 4. Now that used to be a p up there. And 4 over 2, which gives me the interval 1 to 2, and that is the domain of A. So there we have part C of this problem finished. I want to look at the graph of this next, and that's what I'm going to write up right now. So the graph, get my G there, the graph. All right, on this one, I will choose the following window. Now the first part of the window is the x values, or the x range if you like, and that in fact is the domain of the function. I probably shouldn't have used the word range, but sometimes you'll see that on calculators. 1 to 2 is the domain, so that's always easy to pick. The other part, the range or the y values part that corresponds to A, or A of x if you like, that's a little harder to pick. In this one it's clear that area can never be less than 0, so that's a good choice. And the rest of it is a guess on my part based on a little experiment. Now as time goes on, with certain kinds of equations, you can make a reasonable guess as to the y value range. There is also a calculator function that I'll tell you about later on, which will allow you to do that. All right. Well, here's what you get if you go to the calculator. I'm sure you can check this on your own. We are going from 1 to 2 down here, so there won't be any y-axis appearing because that appears back at 0. We do have a piece of the x-axis because we're starting at 0 and going up to 1. Now if you graph this curve, it ends up looking something like this. There's obviously a local max or local maximum at the top here. That's what we were hoping for, a local maximum of the area. Now that will correspond down here to the point, if you use trace on your calculator, to about 1.33. And that again is truncated. And we'll talk about truncation later, but that's cut off after 2 decimals. And the point up here, of course, is the actual maximum height of this function. Now what is this function again? This is the area function, A of x. The maximum height, and that is approximately 0.769. So this point down here is where the local maximum occurs, and this is the actual local maximum value. All right. Well, that's the end of that problem. And I think what we'll do now is pose you a problem, a further problem, that you can go ahead and look at in your own time, and then I'll come back and show you how I would have done it. All right. Here's the problem. Example. A company makes a cylindrical aluminum can containing 500 centimeters cubed. Now you have to realize that that is a measure of volume. So it's clear that we're looking for the volume of this aluminum can. What are we given? We're given that the top and bottom cost 0.05 cents. So that's 0.05 of a cent per centimeter squared. And the sides cost 0.02 cents per centimeter squared. Centimeter squared in each case measures area. So we have information about the area of the top, bottom, and sides. Now what are the questions? First question A, express the cost C, so we're looking for C now, of the material as a function of the radius R of the can. So somehow we're going to have to get a relationship between C and R. That'll be part of our job. Secondly, part B, estimate the value of R that will give the least cost. Among all the possible radii for such an aluminum can, which one will give you the smallest cost? Now that's what businesses are interested in after all. And finally, find out what that least cost is. So, it's time for you to look at this problem, and after you've had a chance to work on it for a while, we'll come back and I'll show you how I would attack it. Now we'll go on with the solution. I hope you had a good chance to work on that problem. Here's how I would attack this. First of all, I'm going to make an observation about volume, because that's what happens in the first sentence of the problem. If you recall the problem now, in the very first sentence it says a company makes a cylindrical aluminum can containing 500 centimeters cubed. That's a volume statement. So before I go any further, I'm going to make some volume observation. So let me go ahead and label this observation 1. Now you might not be so formal about it, but you will certainly need to make this observation. And another important thing in these problems is you need to draw a picture, absolutely. So here is a cylinder, and I will mark off the two important measurements in a cylinder, the radius of the top, if it's a circular cylinder like this, and I'll use a letter, say H, for the height of the cylinder. Then I will remember what the volume of a cylinder is. Volume of a cylinder. The volume of a cylinder, well, let's see, we need a letter for that, so let's call it V. Just make these choices as we go. And the volume of a cylinder will be cross-sectional area. That is, the cross-sectional area in this case would be either the top or the bottom, and that is a circle, times height. And in this particular case, the cross-sectional area, as I said, is a circle. The radius of the circle is r. So we have pi r squared times h for the height. Now there's a formula for volume. I hope it will be useful. I trust it will be, because it's mentioned in the problem. I have a little more information, though. Here, we know that the volume is given to be, the volume we want the can to be, is 500 centimeters cubed. So, since volume in general is this formula up here, pi r squared h, and we want it to be 500, of course they need to be the same. So pi r squared h must be equal to 500. Now I don't know what I'm going to do with that just yet, because after all the question of the problem is about finding a cost, and cost is not mentioned here, but this is certainly an important piece of information that I want to keep here. And I might note that this is in the correct units, in case you're wondering. Units are important in these practical problems. The units are, pi has no units. Pi is a perfect number, so maybe I'll use that symbol as a number symbol. We're multiplying it times centimeters squared, because radius is in centimeters, times centimeters, which is what height is in, and what was 500 in? 500 was centimeters cubed. So you see the centimeters squared times centimeters is centimeters cubed. So in fact, the units work out the way they're supposed to. Okay, good. Well, let's move on and see what else we can say about this. I'd like to get to cost right away, but there's just too much information I need to write first. So observation 2. I made my observation about volume. Let me make another one now. This one is that the cost is for what? It's for area. It's for area. Area of the sides, area of the top and bottom. So that means I better find out what those areas are. Well, again, let me draw my cylinder here. Here's my cylinder. The top radius, as before, I'll mark as r, and the height as h. Well, let me take the two easy parts of the can, the top and the bottom. They're both circles, and they're both the same. So top will be this one, and the bottom will go up here also. The top will be a circle of radius r. The bottom will also be a circle of radius r, same size. And the area in each of these cases is, of course, pi r squared. So the area is pi r squared for each. Now, what about the side or sides of the can? Well, here's a clever way to think about this that's really quite simple. And it takes its idea from this picture. Now, here I have a piece of paper. What I'm going to do is I'm going to roll it up, and you see what I have here, a cylinder. This is a cylinder without the top and bottom. And if I let the paper go, you see it breaks up into a rectangle, a single rectangle. Now that is the idea I'm going to use here. I'm going to imagine that I take my cylinder and I split it down the side. That's what that dotted line will mean. So I'm going to split and I'm going to open it up. Split and open up. So what will I have down here? I will have a rectangle. And the rectangle will have vertical dimension h. Now that's to correspond to the height here of the cylinder. And then the horizontal dimension corresponds to the distance round the cylinder, which you know is circumference. And circumference, of course, is 2 pi r. I'll even write the word out here. Circumference. So that means, just for the record, the area inside here, of course this is a rectangle, so we just multiply the two. We can multiply them and get 2 pi r times h. So now I have all the three areas involved, and now I probably have enough information to construct a cost function. So these observations set aside and kept in mind, we'll now go ahead for part A, see if we can come up with cost, which we'll call C. Now cost, just for the record, is in cents. We'll want to check our units as we go. And how are we going to compute cost? Well, start simple. Don't try to get too complicated in the first iteration of this. Just say the cost consists of the cost of the top and bottom, which luckily are the same, and so that's plus the cost of the side, or sides, depending on what you want to call it. Now, we don't have either one of those costs. What we have are something that we can base the problem on, but we need to do a little bit of calculation here. So, here's what I'm going to say. Here's the idea behind what I'm going to do. Cost can be thought of as area over the number 1 times cost per area. Now you see that that's perfectly correct. The areas you think of as canceling, and that leaves you with cost on both sides. What's good about this is we have a formula for the area, and we were given the cost per unit area. So with these two pieces of information, we can replace each of these costs by a product using the information we have. So this kind of analysis, which in units would be cents is equal to centimeters squared over 1 times cents per centimeter squared, where I've just replaced the variable names here by their units. This is sometimes called dimensional analysis. But what we want here is to use that cost per unit area that we got given to us in the problem. Okay, with that observation, I can now rewrite the cost function by rewriting each of these costs as a product. So cost, C, will be area of top and bottom. This is part of the product, times cost per unit area. Plus the same thing for the area of the side or sides times the cost per unit area there, which is different. So now I finally have the cost equation written in pieces that I have given to me or can calculate, as I've done in observations 1 and 2. So now I can go and write, what is the area of the top and bottom? If you remember, the area of the top and bottom were the areas of two circles. So that was 2 times pi r squared, which is the area of one of the circles, times the cost per unit area, if you recall, was 0.05 cents. And then we add to that the area of the sides, which we wrote as 2 pi rh, if you remember the picture, times 0.02, which is the cost per unit area given to us in the original problem. So if I multiply things out a little bit further, I have the 2 times 0.05. Now that gives me 0.1 times pi r squared, plus, and here I've got 2 times 0.02, so that's 0.04. So that's 0.04 times pi r h. So if I bring the c back down, I can now box this in and say, yes, I have the cost function. Now there's only one problem with this. If we read the original problem, let me bring that back for the moment. Express the cost c of the material as a function of the radius r of the can. Well, let's see what we have here. The cost is expressed as a function of r and, unfortunately, also h. So what we need to do is get rid of the h. We need to replace it somehow by a function of r. Now this is where we recall one of the observations we made and use it here. Recall observation number 1. From observation number 1, we got that pi r squared h was equal to 500. We were not sure yet there where we were going to use it. But now we know we'd like to have r in terms of h. Or rather, I'm sorry, h in terms of r. So we'll simply solve for h. So h will be 500 over pi r squared. That's exactly what we need now. So now I bring the cost function back. The cost is 0.1 pi r squared plus 0.04 pi r. And now let's put h in there. H is 500 over pi r squared. Now this raises all sorts of questions of cancellation, so let's go ahead and do those. I would like to mention that this is now a function of r, so I'm going to write c of r instead of just leaving it as c. So a little bit of simplification. 0.1 pi r squared, nothing I can do there, plus, now let's see what we can do here. Of course the pi's are going to, pi over pi is 1, so that will cancel. R over r squared, one of the r's will go away, leaving 1 on the bottom. So we'll have a single r on the bottom. What about this 500 and the 0.04? Well, the key is to remember what 0.04 means. It means 4 100ths, if you can see that squeezed in there. That's 4 100ths. Well, 4 100ths times 500, the hundreds cancel, and then you have 5 times 4, and so you have 20. So there's the cost function. This is a function of the radius r. That's what I wanted to do, and now I've done it. Now what I want to do next is look at a picture so that I can see a minimum, because that was what we wanted to do in part B of the problem. Let me bring that back for a moment. You maybe put it up here so you just see B. There's B. Estimate the value of r that will give the least cost. Now to do that, we're going to use a graph. Then find that least cost. And that again, we'll use the graph. But before I do that, let me go ahead and give you a technical note. So this is a technical interlude, if you like. This is just something that, here's a perfect place to bring it up, so I will. It's another aspect of your calculator. If you haven't already learned this, you can try it out now. On a calculator, what you can do is first you can enter a function, as you've always done. You can then choose an x interval for your function, and of course that corresponds to a domain. And then, remember that when I talked about functions earlier, I said domains are usually easy to find and calculate. Ranges are harder in general. However, we need a range if we're going to see the complete graph of a function on a screen. So how do we get the range? Well, we can do it algebraically with a little bit of work and a little bit of experiment going back and forth between the calculator and the algebra, or we can use a nice feature of calculators. Then, something called autoscale, or some calculators will call it zoom fit. You'll also see, or I've seen at least once, zoom auto, etc. Any one of these commands, now your calculator will only have one of them, but whichever command you have What will that do for you if you then apply that to this function on this x interval? It will automatically, now this is what the auto part means, automatically calculate, I'm writing this all out so you can think about it, calculate the value of the function, the one that you entered, at each pixel of that x interval. Because remember, the x interval on the calculator, if you remember when you look at the calculator screen, all the points along the x interval are little dots, and those correspond to pixels, picture elements, and the calculator can only work with them. So for each one of those x value pixels, it will then calculate and choose the y interval. Now remember, that's going to correspond to the range. That will show the entire graph. Now, you might say, this is great. All I have to do is pick out the domain, which I know how to do in almost every case, type that in along with the function, and then hit this auto scale or zoom fit or whatever key, and suddenly I will have a graph, after the calculations are done, on which the entire graph appears. I have the highest point, the lowest point, and everything else. Well, surprisingly, although that does sound like the be-all and end-all of graphing, it turns out that very often it's not very helpful. The screen gives you more than you'd like to know. So you still have to use common sense in graphing these. So I wanted to point this out because this was something we hadn't seen before, and you might find it useful here. Now, I'm not going to do it. I'm just going to show you the resultant graph. But when you do this on your own, you might want to try that. Okay, continuing on with the problem, part B, I'm going to do this via a graph. And the window I've chosen is 0 to 10. The upper limit is, again, a guess based on experience and looking at the picture. And the upper limit in the other case is also a guess. So let me be frank about that. The more you know, or the more you use autoscale, you'll be able to come up with better and better guesses. This stands for R, the radius. This stands for C, which is C of R, the cost. Here is the graph, and those are the axes there, going from 0 in both cases, 0 to 60 in the y, 0 to 10 in the x. Here's what the picture looks like, more or less. There is a local minimum here. Of course, we were looking for minimum cost after all. Remember, this is the cost function, C of R. We're looking for that minimum, and by using trace or other functions on your calculator, you can guess this to be about 3.16 centimeters. And then where it corresponds on the y-axis, of course, that is the actual least cost, which we were asked for, and that is approximately 9.46 cents. So there we are. We've answered both of the questions we were asked, and now we've finished this particular problem. Finally, before we end up Unit 2 here, I want to make a couple of remarks. Part of the difficulty in learning to do these sorts of word problems, these mathematical model problems, is deciding what to do when. And I think what students need to do more often is some of the following notes. Now, this is just advice. Listen to the questions. I ask myself. Too often, students will write down what I write down, but not write down what I say. And what I say more often than not is more important in finding out how to work your way through the problem. So listen to the questions I'm asking myself here on the tape. Secondly, let the problem guide you. Don't be fixed on a particular method that you remember from some other problem. It's more important to remember the ideas involved. The problem will be slightly different in every case. Ask small questions. Don't try to solve the whole thing at once. Ask small questions. You might say that you will be working on partial problems. What I did in that problem with volume, I looked at the volume information. I got it. I didn't know what use it would be at that point, but I wrote it down and went on. I got the area information, and then I discovered how to break the cost up. All of these were small questions or partial problems. You should do that, I think. Remind yourself constantly of what it is you're looking for. In a long problem, you can forget. So remind yourself constantly of the question or questions being asked. Now, I put ... because there's lots of other advice, and there'll be some advice that you want to construct on your own, based on your own experience. But that will allow us to finish up Unit 2 now, and when we come back, the next time you see me, we'll be starting an entirely new unit.